this video, we will discuss the radiation fields obtained from a Hertzian dipole antenna. Hertzian dipole antenna is also called as infinite sphere oscillating current element, whose length is very less. So the length of the antenna is about 0.1 lambda. So lambda is again equal to C by F for any operating frequency of the antenna. The lambda can be obtained. That we can decide the length of this Hertzian dipole. So if we consider this scenario, this is the length of Hertzian dipole antenna. Small differential length is considered for the analysis. So radiation from this Hertzian dipole antenna at this point P of r comma theta comma phi is to be estimated now. Okay. So the distance between this Hertzian dipole antenna and this point P is said to be the distance r. So again, this phi is nothing but azimuthal angle, theta is a polar angle. So this Hertzian dipole is placed along the z-axis. It is running from minus dl by 2 plus dl by 2. So the derivation is actually started from the potential at a point P. So at this point P, first we have to obtain the potential value. From that, we are able to obtain the field values, that is magnetic field and also electric field. So the potential at a point P can be given by AZ. Z indicates the direction in which the Hertzian dipole is placed. The suffix AZ. So it is nothing but mu by 4 pi volume integral of J of r dash by r multiplied by e power minus j beta r dv. So this P indicates volume integral. This J indicates the current density. In this particular current element. And e power minus j is the phase factor which is added along with the magnitude factor. So in this phase factor, this beta is nothing but the propagation constant, r is the distance from the point and the Hertzian dipole. dv is again volume derivative. So this is the general formula for the potential dv point P. So here, since we all know that this is the Hertzian dipole was very small in length, the density is not necessary to be calculated. Instead, we can calculate the line current itself. The current flowing through the antenna is assumed to be line current. That is sufficient for calculation. So that for the Hertzian dipole, the volume, the current density can be reduced to this line current, and volume integral can be reduced to line integral. Okay. So that is the substitution made here. Mu by 4 pi is kept as C. The volume integral is now replaced as line integral, which is running from minus dl by 2 to plus dl by 2. So that's why the integral is from minus dl by 2 to plus dl by 2. Current density is reduced to line current, and r is replaced, capital R is reduced to small r, e power minus j beta r dl. This dv is reduced to dv. Volume integral is reduced to line integral since the length of the dipole is very small. So next, just we are integrating this particular term along this dl, then this plus dl by 2 and minus dl by 2 upper and lower limit will substitute, and we solve it, we will get this equation. dl is the resultant answer. So the final Hertzian final potential at this point P is given by mu Im by 4 pi r e power minus j beta r dl in the direction of AZ. Okay. So everything we have calculated in terms of Cartesian coordinate system. But in reality, the point P is assumed in a spherical coordinate system with 3 points r, theta, phi. R is the distance between or radius of the sphere in spherical coordinate system. Theta is the polar angle. Psi is the azimuthal angle. So this AZ has to be mapped or transformed to the spherical coordinate system. So for that, Cartesian to spherical coordinates mapping has to be done. It has to be transformed. So for that, these transformation equations have to be considered. These equations are generalized equations. To transform AZ from AZ to AR, we will use this relationship. AR will be equal to AZ times cos theta, and A theta is nothing but minus AZ times sin theta, and A is 0. Okay. And next step, we will substitute AZ as the equation we have obtained in the earlier case. So this is the reduced form or transformed form of potential equation in r, theta, phi coordinate system. Next, we are going to derive the magnetic field component H vector from the Hertzian dipole to a certain point called P. So previously we have obtained the potential AR, A theta, A phi we have calculated. From that we will be obtaining the magnetic field component H vector. So H vector can be obtained by applying curl on the A vector. The curl is applied on the A vector in order to obtain this magnetic field component. Okay, so 1 by mu multiplied by del cross u. So when applying the curl on the particular vector, any vector it may be, it can be expanded to determinant form. So this is the determinant format, the general determinant format for spherical coordinate system. So for in case of Cartesian coordinate system, this determinant will be. So always in this determinant, the first row will be comprising of all the unit vectors. For example, in the spherical coordinate system, the point is r, theta, phi. So in r, theta and phi, in both directions, all the three directions, unit vector will be available. So first row is all about the unit vectors present in all the 3 points. So the first is AR, unit vector direction of R. Next is R into A theta. Next R sin theta into J. So first row is full of the unit vectors with respect to the individual point. Second row is full of the derivatives of at the corresponding points. Dou by dou R to the first point, then dou by dou theta to the second point, and dou by dou phi to the third point. And the third row is full of the corresponding potential values or voltage values at this particular point. So AR, R into A theta, R sin theta into U. This is the general form of the determinant the spherical coordinate system multiplied by the term called 1 by r square sin theta. Okay. Next step is to expand this determinant, that's all. So 1 by mu r square sin theta will be as it is. So if you expand this determinant, first we will be expanding for the first row and first column. We all know that if we remove this first row and first column, this term will be and if we just cross multiply this term as r sin theta a phi into dou by dou theta. We all know that just a phi is 0, isn't it? That's what we have seen previously. So a phi is 0. This term will be completely 0. Again, if we cross multiply these two terms, dou by dou phi into r into a theta. So a theta equation, if we refer, a theta equation does not contain any term involving phi. So a theta, this particular derivative will be also 0. So the first term will be completely 0. Just cross multiplying, we are cross multiplying, and we have observed that that term does not exist. Next is r into a theta. For the next row and the second column and the first column, the second column and first row, if we eliminate, we can get this component. Again, dou by dou r into r sin theta a phi. A phi is 0, so the first term is 0. And if we cross multiply these two terms, dou by dou phi times AR. Again, in the AR equation, there is no term involving phi. So again, this term will be also 0. So r into a theta is also 0. And the third term, r sin theta, r into sin theta a phi. For the third term, if we eliminate this particular corresponding rows in columns, this term will be existing. Dou by dou r into r a theta, that term is present, minus dou by dou theta into AR, that term is also present. Okay. Why? Because a theta has certain components involving r. So it is present. Again, AR also has certain components involving theta. So only these two components are present and we have the other two terms will be 0. And if we just substitute the a theta, AR value, what we have got previously here, and if we just take derivative on the r part by maintaining the r other parts as constant, we are differentiating the r terms only, we will get this particular answer for the first term. It is mu im ds sin theta, everything will be constant. B e power minus j beta r term is actually differentiated. We will be getting e power minus j beta into j beta. Upon solving this, we will get this particular term. First term. For this first term, we will be getting this particular. Okay, next. Dou by dou theta times AR. Again, substituting AR and differentiating only theta terms by maintaining the R term as constant, we will arrive into a solution like this. Mu im dl e power minus j beta r by 4 pi r into sin. Again, only the third component is exist and the third component is in the direction of A. So we can write Phi as a suffix for the magnetic field. So magnetic field is present in the direction of phi. So next we are just taking the common parts as outside and maintaining the individual parts here as well. And upon just reducing the terms, we will finally arrive into a magnetic field component equation as Im dl e power minus j beta r sin theta divided by 4 pi multiplied by j beta by r plus 1 by r square. This r term is taken inside this bracket for our simplification. And it is present in the direction of phi. So magnetic field component has been obtained, which is radiated from the Hertzian dipole antenna, which is in the direction of phi. So next we look into the electric field component derivation. Next to the magnetic field, from the obtained magnetic field, we can obtain this electric field. For that, we will use the known Maxwell's equation, that is del cross H is equal to J plus J omega epsilon into E vector. Here J is nothing but the current density. The current density is assumed to be very negligible or zero for the case of Hertzian dipole and in free space condition. So J will be equal to 0. So resultant equation will be del cross H is equal to J omega epsilon times E vector. So here we have H vector but we need E vector. So we can rewrite the equation as E vector is equal to 1 by J omega epsilon times del cross H. Here already obtained H phi equation we already have with us. In this H phi equation we are going to apply curl on the H phi equation that we have obtained already. Similar to that derivation of H vector, here E vector is also derived in similar way. Expanding this del cross H to the determinant by consisting of all the unit vectors in the row and all the derivatives in the second row, all the corresponding potential equations in the third row, magnetic potential equation in the third row. Again, H phi is present. H is present in the direction of phi. So if we consider any point with the three directions, namely some r, theta and phi. So H is assumed to be present in the direction of phi. So H is present in this direction, so we are indicating it as H phi. So we can readily say that E vector will not be present here because whenever the electromagnetic waves propagates, both electric field and magnetic field will be perpendicular to each other. So if the magnetic field is assumed to be present here, electric field will be perpendicular or orthogonal to this magnetic field only. It will not present in this particular direction at all. We can ensure that this E field will not be present in this particular phi direction. So E phi will be 0. Okay, and then H is present in this direction. Orthogonal to each other, we have two more directions, that is R and theta. Either in these two directions or in any one of the directions orthogonal to the phi direction, E field will be present. So E field will be present either in R direction or theta direction. So that's what we are going to obtain it here. And one more point to note that here H phi is present. Then in this direction, H will not be present because already H is available in this direction. So in this direction, H will not be available. Similarly, in this direction also, H will not be available. Because in this particular coordinates, with respect to this H phi, only E field will be available. So we can say that H theta will be 0 here. Next, we are expanding this determinant in order to obtain the final value of fields. So by expanding this particular determinant form, we arrive to a form that AR and A theta fields are existing. So E field is a combination of ER and also E theta field here. So individually we can derive the ER term and E theta term separately, similar to the previous derivation of magnetic field. So here ER, AR. This ER term is nothing but the term involving this rho by rho theta r sin theta H by. Again, this E theta is nothing but rho by rho r sin theta H by. Instead of H phi, we have to substitute the value that what we have obtained earlier in the magnetic field equation. We have to substitute that particular H phi equation and we have to proceed further. We have to again apply the rho by rho theta to the terms involving theta and we have to take all the other terms as constant. And if we proceed in that way, finally we will arrive into this equation for VR, that is Im dl e power minus j beta r times theta. Here a new term eta is introduced here. So eta is here is nothing but beta by omega epsilon. Upon deriving step by step, we will arrive into a term called beta by omega epsilon. That is replaced as beta, that is intrinsic impedance value. So again, rather values of 1 by r square plus 1 by j beta r2 times cos theta in the direction of AR. So we have obtained the electric field component in the direction of R. Again, we can derive for the second term also, and finally we can obtain the EP in the direction of theta also. Similarly, d theta will be equal to Im dx theta sin theta into j theta by 4 pi multiplied by 1 by r plus 1 by j beta r square minus 1 by beta square r2 times e power minus j beta. So all this equation is available in the direction of theta. So this is regarding the electric field component derivation. Okay, finally we have obtained all the three equations, that is electric and magnetic field component. Electric field component has two equations in the direction of r and theta. Magnetic field component has available in the direction of phi. So these are the three equations we have derived so far, which by ER and E beta equation. So with these equations, we can again reduce these equations for near field and far field conditions. So let me just tell you that what is near field and far field conditions. So consider any antenna structure like this. So we will have a certain range of coverage to a certain area limit. So we first design the threshold region to differentiate between near field and far field region. So near field and far field region. So before getting to detail about near field and far field region, we just want to first identify the threshold distance which differentiates this near field and far field region. So let us assume this is threshold distance from this antenna, that is beta r equal to 1. So when beta r equal to 1, beta is the propagation constant, r is the distance between the antenna and the user. That is the reference distance. If it is equal to 1, r will be again equal to 1 by beta, and beta we already know it is 2 pi by lambda. If we substitute here, it is lambda by 2 pi. So approximately the r distance is about lambda by 6. So with respect to the frequency of operation of this antenna, this lambda will vary. So based upon antenna frequency, the coverage range also will tend to vary. So here r approximately equal to lambda by 6 is the reference distance to differentiate the near field and far field region. So this is a circle which is drawn for the condition of beta r equal to 1. So we can say the region that is lesser than this particular circle are called near field regions, and the region greater than this particular area are far field regions. So we can categorize near field region and far field region similar to this particular conditions. So beta r is very less than 1, which means the area that is lesser than this threshold distance is called near field region, and the area that is greater than this threshold distance is called as far field region. So why we need to concentrate on near field and far field region distance? We have to only obtain what are the field components actually present in near field condition and far field condition. That is the requirement here. So under near field conditions, what are the elements present? So look at this particular general equations, H phi, ER and D theta. In the near field conditions, all the fields will be available at this 1 by r terms. All the reciprocal of the distance terms, we have to focus on the reciprocal of the distance term in order to understand this near field and far field conditions. So under near field conditions, the terms contributing to the near field conditions are the terms involving 1 by r square and 1 by r cube. Okay. So 1 by r square and 1 by r cube are the terms that contribute to the near field radiation. So in near field, radiations will be very minimum, but there will be a lot of inductive field and capacitive field will be available. So 1 by r square term indicates the inductive field. This is mostly an inductive field. 1 by r cube term is mostly an electrostatic field. So inductive field is a field generated by the antenna due to the reflections coming back to the antenna. That is called as inductive field. Inductive field is all about the reflections coming back to the antenna and loading the antenna into. That is particular field is indicated by the term 1 by r square. Again, 1 by r cube term is a term that indicates electrostatic field. Electrostatic field is a field that is exists in a free space due to the static charges present in the atmosphere. That is electrostatic field. So we will be rewriting the same set of equations again in a reduced form for near field conditions. So if you look at near field equation of ER, this is the general equation of ER, isn't it? From this we are rewriting this particular ER equation. So what we have written, we have neglected this 1 by r square term, we have taken only 1 by r cube term. If the component contains, if the field component contains both 1 by r square term, 1 by r cube term, the higher order term can be considered. So here 1 by r square and r cube are present, the higher order term r cube is considered for the near field effect. So it is rewritten like this. Similarly, E theta equation is a general E theta equation. This term again exists similarly here. Only this Q term is taken. All other terms are neglected for near field conditions. Okay, but this constant term will follow for all the conditions. Only this 1 by r square reciprocal distance term only has to be neglected or included based upon near field or far field conditions. So here E theta is reduced like this. IM dl theta sin theta by remains constant. Again, this particular term exists. Minus 1 by beta square r cube is exists. Minus it is written here 1 by beta square r cube is written. And this term also will be. Will follow as this. Similarly, for H5 equation we have 1 by r term, 1 by r square. In near field conditions, 1 by r term will be ignored, 1 by r square term alone will be considered, and we can rewrite that particular term only for near field. Again, for far field condition, beta r is very much greater than 1. That is the region far away from this particular beta r equal to 1. That regions we call it as a far field regions. In the far field regions, the fields are mostly radiating. So the radiating fields are nothing but r term. So r term indicates radiating field. This is the radiating field. So in the essence, we have to understand that whenever the news is available near to the antenna, the fields, the prominent fields are inductive or electrostatic. When the user is far away from the antenna, the fields are radiated. Okay. So then, similar to this particular near field equations, we can rewrite this far field equation also. Here, the same E theta equation has been considered here, and only 1 by r term is taken, all other terms are eliminated, and this particular equation is okay. And if we check for ER, we can see that there is no 1 by r cube. So we can say that ER does not exist in the far field condition. In far field condition, ER is equal to 0 because it does not contain any term as 1 by r. Again, for H5, we can ignore this 1 by r square term, other terms can be written for H5. An interesting property is that if we divide this E theta and H5 field in the far field condition, then we can also obtain the intrinsic impedance beta. If we literally divide these two equations, only this beta term will be available. All the terms are equally available, so we can cancel that. Finally, we can say that E theta by H5 is nothing but beta. So in this way, we can obtain the radiation from the Hertzian dipole antenna and its near field and far field conditions.